Okay, I had you finish up that one problem and asked you to have that for me today. And I also had sent an email out about that, just as a little help, a little guide. Did most of y'all get that? Okay. Did it make sense? Okay. All right, so if you have that, please just kind of like group them together and get them to this center table, and then we'll just get them all down here. Y'all ready?
Sure.
Everyone got them? Anyone else? Oops, sorry. All right, that everybody? Okay, so we're going to graph another curve today. And maybe one, we might do two, just depends on how long this takes us. And just remember, the homework solution videos have more examples of me sketching curves. So, we could probably do 100 of them and then give you another one that would be different, So they're all unique, but they all have the same basic principle behind them in terms of our approach. All right, so let's do this one. This one looks somewhat interesting to me. I don't think I've done this one out of the book yet. So it's a rational function, but it's not your college algebra rational function. It's a ratio of trig functions, and because of that, it's going to look something like a trig function, but different because of what's going on down here. So let's just go after it. All right. So what would the first step be? Domain, right? Figure out what our domain is. So our domain here is we can't have division by 0, right? I think that's the biggest thing that we would see here as a problem potentially. So we just got to make sure that 2 plus cosine x, right, that can't be 0. And, well, is it ever 0? I mean, you could do this. You could ask yourself when it is, and that means just like move the 2 to the other side. So I want to know when it's not 0, right? So I'm going to try and figure out when it is. So this is me trying to solve the equation. And why am I done at this point? Yeah, the cosine function is bounded between -1 and 1, right? Oscillates. And you're never going to achieve -2. So there's no solution there. And therefore there's no problems, right? This is not going to happen. So we're good. So domain is all real numbers. So I'll put that over on the side here. Domain is, I'll use that for all real numbers, -infinity to infinity. That means my graph exists everywhere, right? Okay. Second step was what? X and Y intercepts. I think we might be able to get the X intercepts. To find the X intercepts, we set the function equal to 0. And that really means all I have to figure out is when sine x is 0, right? Just the numerator. Then we go back to our knowledge of the sine function from pre-cal. And I'm going to look at the unit circle perspective here. On the unit circle, sine is the y-coordinate, right? And the y-coordinate is 0 here and here. So that's going to happen whenever our angle is 0 or pi or 2 pi or 3 pi or any multiple of pi, right? There's an infinite number of x-intercepts in this graph. So I'm going to put here x is equal to n pi, or pi times n, or pi times k. It depends. Some pre-cal instructors use k instead of n. Is that okay? Pi times n, where n is an integer. So n is either like 0, 1, or -1, 2 or -2, 3 or -3. We good? Okay. So that's where we're going to have x-intercepts. Y-intercepts, well, we plug 0 into the function, right? F of 0. And when we do that, we get, sine of 0 over 2 plus cosine of 0. And that's just 0 because sine of 0 is 0. So we're going to have a y-intercept at 0. Let me put that over here. X-intercepts, we're going to have an infinite number of them at pi times n, and I have a y-intercept. I'm going to write my y-intercept as an ordered pair, as a point. Plug in 0, spits out 0. All right, so far, everything seems to be going pretty smoothly. Yeah? Okay. Third step? Symmetry. All right, so for the symmetry, I'm looking for whether or not it's either even or odd. And I can kind of say neither at this point. And why can I say neither? Any ideas of why I can say neither? Yeah, we already have, look, sine is an odd function, and cosine is an even function. And so if you have them mixed together, you're not going to be able to be just odd or just even. Make sense? Yeah. So symmetry, I'm going to say none. And why? Because F is not odd or even. It's kind of a mixture of both types. So. All right, so no symmetry. What's the next step? I think we start getting into derivatives now, right? Yeah. Okay, so for, asymptotes, yeah, sorry. So for number 4, let's talk about vertical asymptotes. For vertical asymptotes, we have to do 2 limits, right? Limit x goes to infinity of the function. Well, let me actually put the function in there. Vertical, sorry. Thank you. Horizontal. We want to know left and right behavior, so we take the limits. So sine x over 2 plus cosine x. So what happens here? You have, as x goes to infinity, what is sine of infinity doing? What does the sine function do as you go out to infinity? It does that, right? Yeah, this is oscillating, right? So it's never going to any fixed number. And then the bottom is also oscillating. Because if you look at this, cosine is going to oscillate, right? Plus 2 just moves that up 2. So you basically have a numerator that's oscillating and a denominator that's oscillating. But it's always defined. You never have division by 0, right? So what's going to happen with this graph is we go out to the side is that, top and bottom change, numerator and denominator. It's never going to go to a specific number, right? So this limit does not exist. We're not going up to infinity. We're not going to negative infinity. We're not going to a specific point or number. We have oscillation, right? I hope you're all comfortable with the fact that if it was just that, the limit wouldn't exist because of the oscillation. This is just kind of a mixture of those two. So still does not exist. DME. So we don't have a horizontal asymptote. Now what happens if we go to negative infinity? Same thing. So I'm just going to put plus or minus here because it wouldn't matter which way I go. I'm still going to have oscillation in both directions. So no horizontals. How about verticals? There we try and figure out if the denominator would ever be 0. Would we ever get division by 0 in a number on top? We already know we don't get that, right? So none. So this is kind of looking like a kind of boring function right now. Or maybe it's interesting. We'll see. All right, step 5. What's 5? Increasing or decreasing. So time for a derivative. So I've got to use some quotient rule here, right? So I'll do derivative of the top times the bottom minus, what's the derivative of the bottom? Negative sine x times the top all over bottom squared. Now, the numerator looks kind of nasty at this point, but I think it's going to clean up. Let's see what happens here. We distribute this cosine through. We get 2 cosine x plus cosine squared x plus, right, plus sine squared, sine squared x all over 2 plus cosine x squared. And cosine squared x plus sine squared x is 1, the Pythagorean identity, right? So the numerator is going to clean up pretty nicely. 2 cosine x plus 1 over 2 plus cosine x squared. So that's my first derivative, right? I need to set that equal to 0, and I also need to look at where that might be undefined. So what about where it's equal to 0? Am I moving too fast? You all right? It's okay? So set just the top to 0. And that turns into cosine x is negative 1/2. So just moving, manipulating algebraically. So our first derivative will be 0 whenever cosine of x is negative 1/2, and I go back again to my unit circle. I try and figure out where this happens. So unit circle, cosine is the x coordinate, right? So that should happen, there and there. At these two angles on the unit circle, I have an x coordinate of negative 1/2. Agreed? What are those two angles? This one right here, and let's do it in radians. It's not the diagonal, it's not this one.
It's a 6, so it's a 4 pi over 6.
No, you're right. 2 pi over 3, it just reduces. 2 pi over 3, there we go, 2 pi over 3. Were you counting your way around?
Yes.
I'm very happy to know that you were doing that.
That's like the way.
Okay, I'm glad to hear that you're doing it that way. Okay. So this is 2 pi over 3. This one is 4 pi over 3. So, by the way, this is just one answer, right? We need all infinitely many answers. So I'm going to have one answer to represent all the infinite number of congruent angles to this, or equivalent angles.
2 pi over 3 times pi to the n.
Plus 2 pi n.
2 pi n.
Plus 2 pi n. So it's this angle plus any full revolution that would get you back to that angle. And then we need this angle plus any full revolution that would get you back to that angle. So x equals 4 pi over 3 plus 2 pi n. Any questions on that part? Are we good? We have an infinite number of places where our first derivative is 0.
That's how many points we're going to plot?
Yeah, we're going to have to plot those on a number line now. So I'll go ahead and leave and come back end of the semester, and we'll have our final. Okay. We good? All righty. Well, feel like I'm missing something. No? Let's do a number line. Let's do it. Yeah, well, I didn't do does not exist. Now, I did, but I did it mentally, and I should have stated that. I'm not even looking at where the derivative doesn't exist, because the derivative, the denominator, is equivalent to, the denominator is the same thing as what we had in the beginning, right? So it's it's never undefined, right? I mean, you're never going to have division by 0 here. This square doesn't make a difference, does it? Right? This is still never going to be 0. So if we want f prime does not exist, doesn't happen. Okay, now number line. And yes, we're going to run into a problem because there's an infinite number of points. So let's put our critical numbers here. Let's start with 2 pi over 3. So let's just make, just so we know where we are, let's put this as 0 right here, okay? Just so we have a reference point. So 2 pi over 3, just going to put it here, 2 pi over 3. So that's 1 pi over 3, 2 pi over 3. Here's 4 pi over 3, right? That's these two. But I'd have to keep going, wouldn't I? So I would have another set of numbers out here, another group of 2. So let's get the next group, okay? Let's get the next group. So what would be the next group of angles that we would have? You would actually have to add 2 pi, right? So you let n be 1, you add 2 pi to this. So what's 2 pi over 3 plus 2 pi? So you get a common denominator, right? Over 1, you multiply top and bottom by 3. If I do that, this is a 3, this is a 6. And so you get 8 pi over 3. 8 pi over 3 would be our next one. And then if we do the same thing here, we should get what? 10 pi over 3, right? 10 pi over 3. So we have 2 more that we could put here. Now, they're not going to be the same space. They'll be the same distance, but they're going to be further down the road here. So it'll be 8 pi over 3 and 10 pi over 3. You get the idea? So maybe now that I have an idea of what's going to happen, like I should be able to get like the next group if I wanted them. Now that I see what's going to happen, I'm going to kind of, just for my own sake, I'm going to kind of redraw this, all right? I want to redraw this because I see that these are all like some multiple of pi over 3. This is 2 of them, this is 4 of them, this is 8 of them, this is 10 of them, right? These are all pi over 3s. So I'm going to make my graph a little bit better, what I'm going to do is start over. Here's 0. And I'm going to count by pi over 3s. So I'm going to say this is 1 of them, 2 of them, 3 of them, 4 of them, 5, 6, 7, 8, 9, 10. You see that? I'm just doing equal intervals. And my first one was at 2 pi over 3. 3. This would be 3 of them. This is 4 of them. 5, 6, 7, 8 of them. 9, 10 of them. Do you see what I mean now? How they're not equally spaced. Like the distance between here and 0 is not the same as the distance between here and here. Now the next group will be the same distance, right? This gap is going to be the same gap we have here. Now, should we do more, or do you want to you're happy with this? Okay. All right. Now what? Test points. Test points. So I've got to pick some test points. I think right here would be a good one. That's pi over 3. That's a bad marker. Pi over 3. I could have picked 0. Here would be 3 pi over 3, wouldn't it? Which is pi. 4 pi over 3, 5 pi over 3, 6 pi over 3. I like 6 pi over 3 because that's 2 pi, isn't it? Y'all following what I'm doing here? 7 pi over 3, 8 pi over 3. 9 pi over 3? 9 pi over 3 would really be 3 pi. What would be a good one to pick down here? 11 pi, 12 pi over 3? Because 12 divided by 3 is 4. So 4 pi? Y'all see how I'm doing that?
Yeah.
Okay. All right, now, where are these points going? I'm testing them. Where am I plugging them in? To the first derivative. Now let me box up the first derivative. All we care about is the sign, right? All we care about is the sign. What can we say about the denominator? Well, it's always positive, right?
Yeah.
So all I really care about is the numerator. What's happening? All right, so let's look at this. Going back to pre-cal. Pi over 3. What is cosine of pi over 3? So there's pi over 3. What is cosine of pi over 3? It's the x coordinate. It's what, though? 1/2? 1/2 times 2. 1 plus 1. It's 2. So it's positive, right? So we have positive, which means that our original function is going up here. What about pi? What's cosine of pi? So at pi, you're here. -1. 2 times -1. -2 plus 1. You get a -1. So that's a negative number. You go down. All right, 2 pi. That means we're here. What's cosine of 2 pi? 1 times 2 plus 1, positive. Looks like it's going to go up, down, up, down. Let's see. Plug in 3 pi, right? So 3 pi here is this, right? So we're -1. So multiply it, you get negative. So it goes down. And then finally, 4 pi is the same as 2 pi. So you get the same thing, so it goes up. Now, we have to imagine that this just continues, right, forever? And that we would get the same answers. Like we would get, as we broke up the next section, right? We would get this up, down, up, you know, and that would continue on. And then we could also go this way forever with the same pattern. So what we're going to wind up doing here is graphing like one section and then just duplicating that section both directions. Okay, I think that's good. Step 6 or second derivative? Was it step 6 was the concavity? Concave up and down? No?
Local max, local min. Yeah.
Oh, local max min. Okay, well, can we see them? We see them?
2 pi 3.
So let's see. I guess we'll write it down. So that's step 6, right? Local max min. All right, local max. Where do we have local max? At every, let's see, 2 pi over 3 and 8 pi over 3. Was that this one? Was that all of these?
Yes.
It was all of these, right?
Yeah.
Because that's where we got 8 pi over 3 from, right? We let m be 1.
Yeah.
So it looks like we're going to have local maximums at all of these points. So local max at f of 2 pi over 3 plus 2 pi n. That's going to look weird. But remember how I asked you to write your maximums as f of the number and then the answer? The reason I did that is because it shows where they happen. Look, we're actually saying we have a maximum at any of these, right? And what is the actual maximum? What's the value? What do we have to do? Plug those into the original function, right? To the original function. So we have to plug in all infinitely many? No, just one of them, right? Because they're all going to give you the same answer. Why are they all going to give you the same answer?
Because it's just oscillating. It's bounded. It's continuing.
Yeah, because whatever sine does, right? If I plug in a number here for sine, then if I add 2 pi to it, it's going to be the same answer because we're going all the way around back to this another angle that's an entire revolution away. So sine is going to be the exact same value, and cosine will be the same value if I go around one time. So let's just plug in 2 pi over 3. So what was sine of 2 pi over 3? That's the y coordinate over there. So root 3 over 2 over 2 plus, what was cosine of 2 pi over 3? 1/2? Negative 1/2? That's bad notation. Should never put plus minus. There. Make sense? Okay, let's clean that up. What's the denominator really? The denominator, negative 2 minus 1/2 should be 3/2, right? 1.5, 3/2. So this is root 3 over 2 over 3/2. And now let's just flip that fraction up. Root 3 over 2 times 2 over 3. 2's cancel. Root 3 over 3. That's our local maximum value. It's going to happen infinitely many times. It's going to happen at every one of these. So the problem that I asked you to go home with and do, right? We didn't have to do any of this, right? That's why I was saying, like, I could do 100 problems and then give you a different one, and it's going to have something different in it, most likely, right? This has a lot of trig. All right, local min. That's going to happen at all those other ones, right? 4 pi over 3 and all of these guys. So 4 pi over 3 plus 2 pi n. All right, let's plug 4 pi over 3 into that. So what is, I'll just draw a quick little reference again. 4 pi over 3, we're down here, right? So what is sine there? Negative root 3 over 2. And then the denominator is 2 plus, and then what's cosine there? Negative a half again. So aren't we going to get the same answer, just negative? Yes? Negative root 3 over 3. All right. Questions at all? What do y'all think of this? Are your like pre-calculus legs kind of wobbly a little bit? Or do you feel okay with this? What's that? Yeah, goes away. All right, well, let's move on to step 7, which I think is where we have to do concave up and down now, right? Inflection points. Oh, crap, I just erased the derivative. It's all right. 2 cosine x plus 1 over 2 plus cosine x squared. Okay, so I have to take derivative of that. That sucks. All right, well, this is a good practice derivative. What's the derivative of the top? Negative 2 sine x times the bottom. All right, that's starting out the quotient rule. Okay, minus the derivative of the bottom. But the bottom is chain rule, right? You got something to a power, so you drop the 2 out first. 2 times 2 plus cosine x to the first power. I'm going to rewrite this here because I'm going to run out of room. Okay, to the first power because I brought the 2 down. Now what? Times negative sine x, which is the derivative of what was in here. But then all of that times the top. 2 cosine x plus 1. I still ran out of room. All of that over the bottom squared. So it's already squared, isn't it? So it's going to be 4th power. That looks pretty bad. That looks pretty bad. But I trust that the author picked this problem carefully so that this would clean up a little bit and be solvable, because I've got to be able to set that equal to 0. See, this is the thing, like in my pre-cal class, we solve trig equations. Like it's part of what we do. But if I walk in there and I give them that equation right there and ask them to solve it, that's going to be pretty frightening looking, right? See, and that's the difference in calculus, is that everything just gets cranked up a little bit, you know? Well, a little bit, a lot, whatever. Right? Everything just kind of like, the things you're messing with, the things you're solving just get more complicated. But the idea is still the same. We just need to try and solve that equation. So why don't we just continue cleaning this up? So I see some common factors. Like I don't want to start multiplying all this all out because I see that I can pull some things out to start. I see a sine in both of these. I see a 2 plus cosine x factor in both of these. And that will help me because I'll be able to avoid expanding this. Now, could you expand that? Yes. And then distribute this? Yes. But I'm pulling a GCF first. So you ready for my GCF? Here comes my GCF. I'm going to pull a negative 2 sine x, 2 plus cosine x out. Do you all agree that both of these chunks right here, right, because they're separated by subtraction, both of those chunks contain that? Okay, so I'm pulling that out. Put a bracket here just to stress that that was a GCF. What is left here when I pull all of this out? Just one of those factors, 2 plus cosine x. I don't have to put it in parentheses, do I? No, I don't. And I'm not going to. Yes?
Can you factor the cosine x squared since there's 2 on the other side? Oh, wait.
Oh, yeah, they're a little off. Oh, man, that'd be real nice, wouldn't it? Yeah. This is a little different than this, so we can't. You know what I thought you were going to ask me is whether or not once we pull this out, if we can cancel it with one of these on the bottom, which we will be able to do. But just I'll do that on the next step. Okay, so we've got this. That's what was left here. Now here, I pulled the negative out, I pulled that out, and well.
Wait, one negative.
Yeah, you want me, okay, I'll pull the 2 out and I'll pull the negative from there, right?
Yeah.
So that leaves me with a minus, doesn't it still?
Yeah.
So I still have a minus. The 2's gone, that's gone, that's gone. So all that's there is this, right? So how do I write that?
It's 2 cosine x minus 1.
So I just need 2 cosine x. Now I either need to put minus 1 here, or I need to put plus 1 and put it in parentheses. I'm going to do that just so everyone can hopefully see what I've done there. So ignore this minus sign for a second, okay? Just ignore that. That's going to be this sign. And try and get a negative 2 out of there. So here's the 2, here's the negative, right? So there's your negative 2 out. The sign came out, and then that guy came out. So all that was left was this. All over. 2 plus cosine x, that quantity to the 4th power. Any questions on that? Okay, so recognizing now that we have a common factor, that cancels here, and that becomes a 3. And then cleaning up a little more, I'll go ahead and distribute this minus sign through for kind of a final version of this. So I have negative 2 sine x out front. I'm going to get rid of the brackets and go back to parentheses. All right, when I do this, I'm going to have 2, and then I'm going to take away 1. So that's going to leave me with 1. Then I have a cosine x, and I'm going to take away 2 cosine x's, which is going to be just minus cosine x. And is that all that's there? Have I accounted for everything up here? In here? Yep. All of that over 2 plus cosine x cubed. So it's not so bad now that it's all cleaned up, right? And now I'm going to set this equal to 0. And then I'm going to figure out where it's undefined, but I already know it's not going to have a problem because that 2 plus cosine x can never be 0. All right, let's do it. What are we, 30 minutes into this already? Okay. All right, so I'm setting negative sine x times 1 minus cosine x equal to 0. What I'm trying to do is figure out where the second derivative is 0, right? And because it's factored, right, already, it's just setting each factor equal to 0. So I can divide out the negative 2. That's gone. So then I just set sine x to 0. And then I set 1 minus cosine x to 0, and that just gives me cosine x is 1. So just those 2 equations. And where is sine 0? So go to your unit circle. Sine is the y-coordinate, happens here and here. So x is pi n again. Didn't we have that earlier? Pi over n, I have no idea why I just did that. Pi n. And then where is cosine 1, which would be, cosine is the x-coordinate, which is here, right? And that's just the 0, and then you could add 2 pi. But doesn't this already cover all these answers? Like every answer here is covered here. So I'm just going to stick with this. All right? Number line? I think I'll keep the second derivative here because I'm going to need it in a second to plug some things into it. So I've got 0 just as a reference. I've got pi, 2 pi, 3 pi, 4 pi, right? Those are my interesting points. Wait, did we have pi n earlier? No, we didn't. I said we did have that earlier. We didn't have that earlier. We had 2 pi over 3 plus.
2.
No, it was 2 pi.
We had an X intercept.
That's where it was. Okay, the X intercepts. I knew I wasn't losing my mind there. I knew I had seen pi n earlier today somewhere. Okay, that was so long ago. It was like 35 minutes ago. Shoot. All right, so here we go. And you know what? 0 is on that list, right? All right, so we just got to pick some stuff here. How about pi over 2? That a good one? This one would be 3 pi over 2. What would the next one be? This would be 5 pi over 2. 7 pi over 2. And, oh, I didn't do one down here. 9 pi over 2. I guess I didn't have to go out that far, all the way out to 4 pi. I could have stopped, but. And these get plugged into this right here. The denominator is always positive. Not because of the cubed. Not because of the cube, but the fact that cosine, the worst it can be is -1. So this 2 will always overwhelm this and be positive. So let's just look at the numerator then. What is sine of pi over 2? So you got to think about what's happening at pi over 2 here. Sine of pi over 2? 1, right? So we have here -2. And then here, what's cosine there? 0, so that's just a 1. So you have -2 times 1, which is negative. Concave down. What about at 3 pi over 2? So that goes with that. At this one, we're down here. So now sine of I should make my pre-calc class watch just this portion of this video, because when I teach, yeah, the whole problem. When I teach, when I'm teaching pre-calc, I always try and get my students to look at the angles this way. And if you're not taught it that way, then this might be like really foreign. Maybe you're used to it by now, but maybe those of you who did have me for pre-calc see now why I did it. I think it makes this sort of thing easy to do, right? So where are we? 3 pi over sine is the y-coordinate. We're at -1. -2 times -1 is 2, and then we're still going to get 0 right there. So positive now. Yeah, so concave up. And when we're at 5 pi over 2, we're back here, aren't we? It's this one again. And then this one right here is 7 pi over 2. So it's just going to keep repeating. All right, we have inflection points at every multiple of pi, right? We're getting changes in concavity at every single multiple of pi. All right, now what?
Inflection.
So inflection points at x equals n pi, or pi times n, at every one of these. Hey, let's go ahead and figure out what the value of the function is there. because I'm going to plot these points, aren't I? So we may as well figure out what does the function look like at pi times n or n times pi. So just plug in pi or plug in 0. It doesn't matter. Any multiple of pi. So I'll do pi. What's sine of pi? 0. Oh, wait. These are X intercepts. Right? Right. These are our X intercepts.
You just said it.
What?
You just said it too.
I know. I said it a little while. We said that's where the pi n came from, right? All right. I think we're ready. Let's put it all together. Let's draw a picture. Boy, Desmos would have done this for us a long time ago. All right, so we're going to do that Bobby table, right? Whatever you want, man. Whatever you want. All right, so what do I put on this to create this table? What am I going to put on this number line to start me out? All my critical numbers, both from the first and second derivative. So I will use 0 as a reference, but remember 0 is not part of my critical, well, 0 is a critical number. It's part of the second derivative being 0. So let me do those first. I have 0, I have pi, I have 2 pi, I have 3 pi. Let's go 4 pi. Let's just stop there. I think that's enough. Those are all critical numbers, right? From the second derivative, so those are going to be part of my table here. And then from the first derivative, we had 2 pi over 3. So we did increments of pi over 3. So I'm going to do that in here. Here's pi. If I cut it into 3 sections, then each of those, this is pi over 3, 2 pi over 3, 3 pi over 3, right? 4 pi over 3, 5 pi over 3, 6 pi over 3, 7 pi over 3, 8 pi over 3, 9 pi over 3, 10 pi over 3, 11 pi over 3, 12 pi over 3. See what I'm doing? Okay, so where were those critical numbers again? 2 pi over 3, wasn't it? 2 pi over 3. And 5 pi over 3? 4. Yeah, 4 pi, sorry. I'm not even at the right place. 4 pi over 3. And then it was 8 pi over 3. And 10 pi over 3. Yeah? I think that's good enough. And now I just come across here. The first row is the information about the derivative. The second row is second derivative. And the last one is going to be just the general shape of the original function. And I'm not going to look over here, okay? I'm just going to start out. Let's start with the first derivative. What was it doing to the left of 2 pi over 3? Was it up? It was up? Oh, I forgot a line here. My 4 pi over 3 straight up. Okay, so to the left of 2 pi over 3, I was going up. And then I was going down all the way until I get to 4 pi over 3. So between here and here, so 2 little down arrows. And then from 4 pi over 3 all the way to where? 8 pi over 3, I should be going up. And then from 8 pi over 3 to 10 pi over 3 down. So down in those 2 little regions. And then 10 pi over 3 on, I should be going up. Yes? And now for the second derivative, to the left of pi, between 0 and pi, I'm guessing down. I was down here. And then between pi and 2 pi, I was up. Then between 2 pi and 3 pi, I was down. 3 pi to 4 pi, up. Yeah? Have I told you all about cartwheels? I've always wanted to be able to do a cartwheel. I've never been able to do a cartwheel. That's why I put my daughter in gymnastics. She did a cartwheel. I was like, yes. I have now done a cartwheel. I did it. My offspring has done it. So I wish I could do a cartwheel, because if I could do cartwheels, I would like do cartwheels in class right here, and then I'd be like, just to get you all excited. So imagine me doing a cartwheel and saying, okay, we good? Yes? All right, what now? Go up each of these columns and figure out which part of those smiles or frowns you're on. So here, we're going to be where? Left side of the frown, so it's got to look like this. Right side of the frown, left side of the smile, right side of the smile, left side of frown, right side of frown, left side of smile, right side of smile. I think you all understood that. Any clarification need to be made there? All right, now, time to draw. Here's my X and Y axes. I'm going to go back to the beginning. We had some X intercepts, didn't we? Weren't they at every multiple of pi?
Yep.
So I'm going to start putting points. Let's start putting the actual points of my graph up here. So this is pi. I have a point here, point here. Oh, and at 0. That is a multiple of pi. 4 pi, 3 pi, 2 pi, pi, 0. All right. I had some local maximums and minimums. My local maximums happened at all of the 2 pi over 3 and the multiples, right? The 2 pi over 3 plus 2 pi n. So here I had a local max. So what I'm doing is I'm putting all the points that I know exist on my graph here. At 2 pi over 3, where was I? How high was I, or low? Wasn't it root 3 over 3? Which is some number, right? I'm just going to put it here. This right here is root 3 over 3. That's how high that is. I'm going to put a point there. That's going to happen there. Where else? Where else am I going to have that same height?
Every 4 pi.
At this one, right? At the 8 pi over 3 is the next one. And that's the only two that are going to appear on this graph, right?
Negative.
And now I need my minimums. Where were my minimums? At the pi's, right? So this is it. I mean, I had no horizontal asymptotes. I had no vertical asymptotes, right? I did have an X. I have my X intercepts here. I have my Y intercept here, right? Oh, am I missing? Hold on. What am I missing here?
The elements.
What's happening here?
Negative 3 over 3.
Oh, it's negative. I'm sorry. It was negative. My bad. My bad. Okay. So look here. Yeah, you're right. We had minimums here. I thought our minimum was 0 for some reason. All right. Those happened here at the 4 pi over 3 and at 10 pi over 3. We had another one right down here. Okay, those are my minimums. Now I'm ready to connect the dots. So I've got to connect from here to here. I've got to look like this. I think it's pretty obvious what this is going to look like. It's going to go like this. And then I got to look like this between here and here. So it's going to connect. And then right there, it's got to start looking like this. So what is that point right there called? Inflection, right? We went from a frown to a smile right there. And then here we're going to go smile it up until we get here, and then we're not happy again. And then we're not happy. And then we start to become happy again. And we stay happy. But tomorrow we'll be unhappy again. So this thing just keeps going, right? It looks a lot like just a regular old sine function. But it's not, right? It's not. There's something else going on. All All right, that's it. Imagine this going in both directions forever. Yikes. That only took 50 minutes, half the class. All right, I don't intend on doing any more of these.
Are we going to get into integration?
A what?
Are we going to get into integration?
We have to do optimization first. And then we're going to start doing chapter 5. When we started this section on graphing, I kind of prefaced it with the whole idea of like, this is somewhat outdated, and like I get why you would not necessarily find value in that. But let's start the next section with the problem that I'm going to completely make up right now on the spot. All right? And I think it'll have a little more value to it. All right, this is the beginning of the next section. All right, let's say that I own a farm or something. And what I want to do is I want to build a fence for some of my animals. This is kind of a classic problem in this section, but I'm going to modify the problem a little bit to make it more interesting. So I've got this pen. We're looking from the top down. I'm going to put animals in here. But I've got some animals that don't get along, so I've got to keep them separated from one another. So I'm going to be breaking up this pen into, let's say, 4 equal pens. All right? Everyone understand what's going on so far? Now, when I make this pen, I've got to decide what kind of material I'm going to make this pen out of. So what I've decided is that along this edge and this edge, I'm going to be, yeah, let's do it that way. Let's do those edges and these sections here. That's going to be the blue there is chain link fence. Okay, that's a chain link fence that I'm going to be using there. That way they can see each other, see out of their pens, all right? But because of where I'm building this structurally to maintain the integrity of the enclosure, these two sides right here have to be made out of some wooden material. It's an exotic wood. It's very expensive. The one that we're going to use. That's right. These animals are important to us. All right? You get the idea so far? All right. So I'm getting ready to hire someone to come out there and build this for me, right? So I tell this company this is what I want, right? So they come back to me with some pricing on the material, right? They tell me that the chain link fence, and I'm making these numbers up because I have no idea if this is accurate information, but they tell me this is going to cost me about $5 per linear foot, fully installed, okay? Fully installed, it's going to cost me $4 a linear foot to put in the chain link fence. That includes the posts and the holes they have to put, everything. It's included in the cost. Most fences are are priced out that way.
Labor and everything.
Yep. Okay, now the wooden fence, because it's an exotic material, this wood is very tolerant to rain and everything else. This stuff is actually going to cost me $9 per linear foot. All right? We're still not to the question. So I, as the farmer, need to make a decision as to how big I want these pens to be. So let's say that when I started this out, I decided how many animals I want in each one, and I have an idea of how big I want each pen to be. Let's say that my need, all right, for this is that each pen must be 2 square feet. No, that poor animals, right? 2 square feet. Let's give them 20 square feet.
Some veal.
Yeah, right. They're just
You don't move around, you make yourself tough.
yeah. All right. So each pen must be 20 square feet. Yes. All right. So now the question. What do you think the question is?
How can I get my maximum amount of space with the materials allotted? Or there?
Close. The farmer. Look, if each pen has to be 20 square feet, I can't change the fact that it's 20 square feet, right? Yes. This pen could be 5 feet long and 4 feet wide, and it would be 20, right? Mm-hmm. And whatever that one is, all the others have to be the same. Yeah. Yes? Mm-hmm. So I could do 5 here, right? 4, 4, 4 here, and I would have it. Yes?
Yes.
But I could also do maybe 10 here and 2 here. Now, I don't know if that would be good for the animal, but 10 here in each of these 2. I'd still get 20 here. Do you think the cost changes
Yes.
if I build it in different shapes? Absolutely, because it's going to change how much red and how much blue you use, right? So the question is, how must this be constructed to minimize your cost? To minimize your cost, right? Now, if you don't care, you just have them build it, right? Make it 5x4 and that's my farmer impression. Is that allowed? Is that like politically incorrect for me to do that? Have I insulted anyone? I'm sorry. I did a little farmer accent, just trying to have fun. I lost my job though.
You can't be insulting farmers.
Okay, so the question, how must we construct this to minimize cost? And the key word here is minimize. See, everything we pretty much have done in Chapter 4, with the exception of Newton's method. Newton's method was showing how to get solutions to things using an algorithm. Everything else we've done in Chapter 4 has been about graphing a function and finding its highest and lowest points, right? The last section was like that and more, right? We could graph a whole function with all this detail. But if we want to find highest and lowest points, we have a way of doing it. So it is possible for us to find the minimum value of something. So this is why this falls into the category of into this section. All right, you ready to do it?
Sure.
Let's do it. That's all the information we have. Let's minimize the cost.
You take the derivative of the pen.
Yeah. So what is it that we're trying to minimize here? Cost. All right? So my first thing I'm going to state here is I need a cost function. Right? I need a cost function. Because if I'm going to minimize something, I need it to look like a function so I can, do derivatives and stuff, right? I need a cost function.
So it'll be feet over price, so it'll be a foot for $5 for blue, and the same for red, right?
Yep, something like that.
Yeah.
We'll set it up. So I need a cost function. We good? We need a cost function. This cost function that we get here in these problems is known as the objective function. It is the function that we are seeking to minimize. Or there are some problems that we may do where we are actually doing the opposite. We're trying to maximize something. In either event, if you're trying to find the minimum of something or the maximum of something, it's called optimization. And that's what this section is about, optimization. But the function we're going to work with to do the actual optimization